ionized array of elements or ions. So you've got like positive, minus, positive, minus, positive. Oh, this would be minus, positive, minus, positive. And it kind of goes out in all directions. That would be a lattice. And so when you take, so ionic bonding is a transfer of electrons. So you've got an atom here and an atom here. This one loses an electron to this guy. This guy becomes negative. This guy becomes positive. But to remove the electron is going to require energy. So that's going to be positive. So then the question is, well, why is it that why would they do that then if that's going to be positive? Because things want to go to more stable energy. And that's because when you have a plus and a minus, then they start to form this lattice, and the lattice energy is extremely negative. And so that's the whole idea behind ionic bonding. Always, yes. All right. And then, anybody need a second on this page? Probably not. Okay. Yes. Okay. I'll give you a second then. All right. I don't tend to ask you a whole lot about greenhouse gases. That was really just their way to introduce different types of bonds and be like, well, why do I care about bonding? And they're like, because greenhouse gases. And you're like, oh, I didn't think about those. Now I want to learn. But I'm not sure it had that effect on anybody. But that was their goal. So a couple things to say there. There are debates going on about global warming. Some people say global warming. Some people say no global warming. Obviously, they've taken temperatures and it's gotten warmer. So, and then other people are like, why is it warming up? We don't know. Some people are saying, well, maybe it's natural. And other people are saying, well, it's because we keep polluting the earth and then we're making it nasty and we're kind of ruining it. So we're not going to get into all of the whole debate about that. But for the most part, people accept that there's global warming. They don't necessarily all agree on why, but they agree there is global warming. One thing to note, though, is that in the winter, CO2 goes up, and in the spring, CO2 goes down. Anybody know why? Yeah, partly because of the gas heating, and a lot because of trees having leaves in the spring and no leaves in the winter. So that's got to do with like, oh my gosh, how did I forget the name of it? It's photosynthesis.
Yeah.
Gosh, that's like what you learn in third grade, and I can't remember the name. So,
I know
all right. Another interesting, well, another thing they put in there that's somewhat controversial is the, what was it? The age of the Earth. They put that in there too. So no, not going to ask you about that either. Different people think different things, and that is perfectly okay. All right. So let's go on to the potential energy. All right. So looking at potential energy, they give you a sort of it looks like a strange formula. It's not really a strange formula. They give you Coulomb's law. And if you've had physics or you're in physics, either you've run across Coulomb's law or you're going to run across Coulomb's law. And it's usually 4 pi E naught Q1, Q2 over either R or R squared, depending on what book you're looking at. And this one, they give you a constant, and they don't, 4 pi E naught is a constant, but here they just give you a number. So they give you, let me make pencil work, 2.31 times 10 to the negative 19 joules times nanometers. And if you're doing, Chibu, do you still have a question?
No, I don't. I forgot to lower my hand. Sorry.
Oh, that's okay. Kevin, you have a question?
I did, but you can go ahead. I can ask later.
Okay. So it is potential energy, but it's really Coulombic energy. And that's because it fits Coulomb's law so well. And Coulomb's law has to do with charge 1 times charge 2. And in physics, they'll call these point charges over a distance, some distance. And that will give you your energy. So they call it electrostatic potential or Coulombic potential energy. They give you a couple different things to call. Which negative number? Oh, that's a good question. That's a 19. Sorry, it looked like a 1A. That's kind of sad. Okay, so when you're looking at this, in order for you to have something stable, you need your energy to be negative. So that negative is good in this case. So this is always going to be the same. So really this part is the only thing that determines whether or not your energy is going to be more or less negative. So you look at two things. You look at one is the charges. And the other one is the distance between the two radii. So we looked at the trend for that before, the trend for the atomic radius. And as you go to the left and to go down, it gets larger. So you have large atoms here and small atoms here. So if you have like 2 large atoms, you're going to have large distance. Because the distance is pretty much the distance between the 2 nuclei. So, and as far as charges go, the charges are just the charge that the type of ion it's going to make. And you can get that from the periodic table. So we're not going to talk about transition metals just yet. So remember the pattern is +1, +2, +3. We're going to skip 1, -3, -2. Sorry about my phone here. -1. And then the things at the end are neutral. So if you take something that's positive, let's say sodium will make a positive ion, and then fluorine makes a negative ion, the charges you would put into that formula are +1 and -1, and the distance would be the internuclear distance, so the distance between the 2 nuclei. And there is a homework question like that. Let me see if I can pull up the homework. All right, so there are a couple of things that they ask you about in the homework. One, does anybody need a second on this page? How to calculate the distance? I'm about to tell you how to calculate the distance, actually. All right, I'll give you a second, chat. Let me know when you get finished, chat.
I have a question, sorry.
Go ahead. No, go ahead.
Is that the little graph for the atomic radius on the side there?
Yes. Yep.
And why'd you put that there too?
Because when you look at the distance, it's the distance between the two nuclei, so it matters how big the atoms are. So if you had two small atoms, the distance is going to be small, and two large atoms, the distance will be big.
Okay.
All right. Still need a second, Chad?
You said two small atoms, the distance will be small. Two large atoms, the distance will be large.
Yes.
Okay, and also, what's the formula in the top right corner?
Oh, it's, hang on, I'll rewrite it.
Okay.
It is energy. Oh, hang on a second. Okay. Energy equals 2.31 times 10 to the negative 19 joule nanometers, Q1, Q2, divided by the distance. All right. So if you have a positive and a negative, let's say you have sodium, which is in group 1, connected to fluorine, which is in group 7, and then you compare it to calcium, which is in group 2, and oxygen, which is in group 6. So calcium would be +2, oxygen -2, -1, +1. Which one of those groups would give you the bigger energy? The bottom, right. That's correct. So this one. And the reason is because they have larger charges. So if you just look at the charges, the top of the formula for sodium and fluorine would be -1 times +1, giving you -1. And for calcium is going to be +2 times -2, giving you -4. So the -4 is going to cause you to have a bigger energy. When I say bigger, I mean more negative. So, all right. And what is D? D is the distance, and that's what we're going to get into next. Now, the question that they'll probably give you in your homework, the first one where they ask you to compare the energy, they're going to give you a couple of pairs of gosh, what are they called? Ions. I don't know why the little words just go away. They give you a couple of pairs of ions. Ignore if you have something like you have like this versus that. Don't worry about the subscripts. They don't matter. So when you come to that problem, I thought that was going to erase part of that. Sorry, guys. I don't know why I thought that. But anyway, when you get to that part, don't worry about the subscripts. You're only interested in the charges in that question, because those compounds that they're going to give you they all have approximately the same distance. So the only thing you're looking at in that first question is the charge. Yes, it's much better. -6 is much better than 6. 6 is showing that there's a huge repulsion. And so obviously you don't want a big repulsion, because then your atoms wouldn't stick together. They do have a chart in the book that looks something like this. It's a very famous chart, and most of the time they use it for hydrogen. So right here, so they have like a 0 area kind of right about there. This is going to be negative, and this is like energy on this axis. So this is going to be the negative area there. This is 0. So this is where you have ignore that, 2 atoms, and they're just the perfect distance away from each other. It's the most stable state. Now, if you take the same 2 atoms and you overlap them so that their 2 nuclei come too close together, they start to repel, and the energy increases to like infinity. And then on the other hand, if you start to take the atoms apart, the more you take them apart, the less energy they have until there's no more energy and the energy goes to zero. So that's what that chart is saying in there, that if you have a positive and a negative, they can come together at just the right distance. And even if it's not a positive and a negative, if you have a covalent bond where they share electrons, the way they share electrons, they can come to just the right distance away from each other as well. All right. And so now let's take a look at the next type of question they'll ask you in your homework. Give me 1 second. Okay. So when you're trying to figure out what D is, so you have basically you have a constant, which is that negative 2.18 to negative 19 or whatever. Then you have Q1, Q2, and then distance. Distance equals the atomic radius of atom 1 plus atomic radius 2 So let's say we have 2 atoms, and we want to know what D is. D is the distance between the 2 nuclei. So the radius is half the diameter, right? So that's just the distance from here to the edge, and from here to the edge. That's why when you the overall distance here, that's just the distance between the 2 nuclei is what that's saying. So they ask you to calculate a question. Oh, they have to give you that. They'll give you the atomic radius for both of them. That is a good question. So
Put the whole food in there. Oh my gosh.
I think somebody needs to mute.
That was spectacular. I have a quick question.
Yeah, go ahead.
In a lot of diagrams, especially for water, H2O, it shows that the atoms are partially, for all purposes, submerged in one another. You're currently giving a diagram of their valence shells, their largest valence shells, brushing up against each other. Do atoms partly, I guess, go into each other? I don't know if you already said this and I missed it, but
it kind of depends on what model you're looking at, and that's kind of a really bad answer, but I'll show you what I mean. All right, so let's say you have water, which is H2O, and this brings us into covalent bonding, by the way. So when you have something that's ionic, that's a metal and a non-metal. An electron is transferred. Okay, and that would be things like sodium chloride. They have a lattice energy there. Then we have covalent bonding, and water is covalently bonded.
Mm-hmm.
And those share electrons. So they do kind of brush up against each other, but you have oxygen here, and hydrogen here, and hydrogen here. In reality, they have what's called a van der Waals radius, which is where they come up against each other, and they don't technically overlap. But what you'll see is the electron will be spinning around one atom and then start spinning around the next and then go back to the first one again. So it's sort of sharing the electron in that way. And in that way, it's almost like they're overlapped because the electron goes from the hydrogen to the oxygen to the hydrogen to the oxygen like that.
So they're playing catch with the electron
Yes,
for all intents and
basically.
purposes.
That's exactly what they're playing.
Okay.
And then with, all right. So covalent bonds are always between two nonmetals. And
Professor,
what about alkali and alkaline? Do those count as nonmetals? Because for some reason my book says metalloids when you wrote nonmetals.
no, those are all metals.
So.
Yeah, those would be metals. Somebody else had a question. What was your question?
It says in the textbook in a chart that nonmetals and metalloids.
Let me look and see if I can see the chart you're looking at. Give me just a second. Let's see here. I'm hunting your chart. Give me 1 second. Yeah, the way they put that's a little bizarre. So you could have a nonmetal and a nonmetal, or you could have metalloids in there. So basically what they're saying is anytime you have a covalent bond, there are no metals present and no polyatomic ions present. So
Okay, thank you.
if you had you're welcome. If you had a metalloid, we'll just put ML for metalloid, and then a nonmetal, that would be covalent. Or if you had a nonmetal and a nonmetal, which you'll see more often, that would also be covalent. The big thing to look for is the thing only metal, or is it a metal and a nonmetal, or is it neither of those? So you're looking to see if a metal is present. If a metal's present and there's something else present, that's ionic. If there's only metal present, that's called a metallic bond. And that kind of brings us into the next type of bond, actually, which is the metallic bond. Anybody need a second on this page? Nope. Okay. Cool. All right. So with metals, let's say we have a block of sodium. And sodium is a silver metal. So you have a sodium and a sodium and a sodium and a sodium. And then you have what they call this sea of electrons. So in this case, the electrons are no longer associated with a particular sodium. It's just they're more or less, Batman, huh? They're more or less associated with the group. They're more like a commune. So you can kind of think of, a commune is a really good way to describe it, because in a commune, nobody owns anything. Everything belongs to everyone. And it's the same thing with a metallic bond. In a metallic bond, you have some metals, and then you have these mobile electrons that move around. And the reason that metals conduct electricity so well is because the electrons will move. And so to get an electric current, you have to have moving electrons. So let's see what else they asked in your homework. All right, one of the questions is which of the following pairs of elements is or are likely to form ionic bonds? And so in that case, you're just looking for things that have a metal and a nonmetal, and those are all the ones that form metallic bonds. You know what? I'm wondering if I do or not. Let me check. Well, I might. And again, I might not.